Okay, good morning everyone. Today we will study further some of the important Jacobians. In the previous lecture, we have seen the definition of Jacobian and the Jacobian of UV W with respect to X, Y, Z. This is given by the determinant UX, UY, UZ, VX, VY, VZ, WX, WY, WZ. If you are given U as the function of XYZ, V as a function of XYZ, and W as a function of XYZ. So these are the cases. Now, if so, this is in this case, you can see that XYZ are independent variable, UVW are dependent variable, and you are finding out the Jacobian of dependent variables with respect to independent variable, that is J. In this case, if the Jacobian of XYZ with respect to UVW is to be found, then that is denoted by J dash. We know the property J into J dash is equal to 1. Then we have seen that if UVW are the functions of XYZ and further XYZ are the function of R, S, T, then this is the composite function, and the Jacobians for the composite functions are given by Jacobian of UVW with respect to XYZ will be given by Jacobian of RST. UVW with respect to RST are given by UVW with respect to XYZ multiplied by Jacobian of XYZ with respect to RST. So this is the composite rule for the Jacobians. Now, I'll write an example over here and then we'll talk about the new type of this Jacobian. X square, okay, x plus y is equal to 2 e to the power r cos theta. X minus y is equal to 2i e to the power r sin theta. Jacobian of xy, Jacobian of r theta with respect to x comma y. How can we find this? In the example number 1 and 2. Yes, anyone? X square plus y square plus u square minus v square equal to 0, and uv plus xy is equal to 0. How can we do this? Anyone? In this case, Jacobian of UV with respect to xy. If yes, how? If no, why?
Sir,
Hmm.
in the first one, we can add those two equations and subtract and get x and y in terms of r and theta, and then find j dash
Okay.
and take inverse of it.
So in the first case, I can find x as a function of r and theta, and I'll get y as a function of r and theta. Yes, that is possible. And then we'll take the inverse. Fine. What about the second one? Okay, what is the problem? The reason why you are not able to find out the Jacobian here. Can you identify?
Excuse me, sir.
Yes.
Sir, if we multiply uv and xy um, 2 and add the second equation to the first equation, then it will be x plus y ka whole square
Mm-hmm.
and u minus whole square equals to 0.
So what?
So, am I audible?
Yes.
So, we can find u in terms of x, y, and v in second equation. uv is equal to x minus xy by v, and then put that value in the first equation.
Okay. So, in short, this is becoming difficult. So, what is the reason why you are not able to find this out easily?
So we are not getting the particular value of x and y,
In terms of,
u and v.
okay. So, what are these kind of functions called? Look, in 12th standard, you have had this kind of equation e to the power x into y equal to 0. Find dy by dx. What were these kind of functions called? First of all, can you take the derivative of this?
Yes.
So what were these kind of functions called there? So x dy by dx plus y into derivative of x1 plus derivative of e to the power xy is e to the power xy in bracket x dy by dx plus y equal to 0. Then you separate dy by dx out of this. So x plus x into e to the power xy dy by dx is equal to minus 2y, and so dy by dx will be equal to minus 2y upon this bracket. What were this kind of functions called? Where you had mixture of dependent and independent variables. You didn't had the value of y in terms of x explicitly. No one. So this type of functions were called implicit functions, where you had the mixture of dependent and independent variable. So in this case, xy plus e to the power xy equal to 0. Y is dependent, x is independent, but the equation is mixture of both of them. You cannot have y as a function of x and go on taking the derivative. So that type of functions are called implicit. Even this function, both of them, these are implicit functions because your dependent and independent variable are mixed. So this is an example of implicit function. So what we are going to learn now is how do we take the Jacobians of implicit function easily. Easily word is very important because there are different ways to do it. I mean, just like combining these two equations, do some addition, subtraction, multiplication, you will get the value of x, but not that way. I want to find out the Jacobian easily, even if the equations are hard to solve for x and y. So our topic is Jacobians of implicit function. So consider four variables u, v, x, y related by implicit functions. So f1 of u, v, x, y equal to 0 and f2 of u, v, x, y equal to 0. Then Jacobian of u, v with respect to x, comma y is given by minus 1 raised to 2. Jacobian of f1, f2 with respect to xy upon the Jacobian of f1, f2 with respect to u, comma v. So now what I do is I take the derivative of that function itself, whatever is the given, I mean whatever is f1, whatever relation is between u, v, x, y. Of that relation, I'm taking the Jacobian. Please note this formula down. Even for explicit, we can use this. Okay. Fine.
So what is the use of -1 square?
It depends on the number of variables, and so I have written it. So in the case where you will have three variables, you will have -1 raised to 3. Generally, what happens is at the time of exam, students forget that there is something -1 raised to for three variables. And so let's keep a habit of writing the -1 raised to number of variables. In this case, there were two, so -1 raised to 2. Now, for three variables, we'll have three variables, so we will have -1 raised to 3. So it will give you -1 there. So let u, v, w, x, y, z be the variable related by implicit function. So we'll have f1 of u, v, w, x, y, z equal to 0. f2 of u, v, w, x, y, z equal to 0. f3 of u, v, w, x, y, z equal to 0. So Jacobian of u, v, w, x, y, z. So this will be minus 1 raised to 3. Jacobian of f1, f2, f3 with respect to x, y, z upon the Jacobian of f1, f2, f3 with respect to u, v, w. Look, the numerator is going in the denominator and denominator in the numerator. And these are the two formulas to find Jacobians of implicit function. Fine. Let's solve some examples now. If u cube plus v cube is equal to x plus y, comma, u square plus v square is equal to x cube plus y cube. Show that the Jacobian of uv with respect to xy is equal to 1 by 2 y square minus x square upon uv 1 minus v. Note that our relation was like this: f1 of u, v, x, comma y equal to 0. So you have to bring everything on the left to declare the function 1. So we will have f1 as u cube plus v cube minus x minus y equal to 0. And f2 is u square plus v square minus x cube minus y cube equal to 0. So the Jacobian of uv with respect to xy is given by minus 1 raised to 2 Jacobian of f1 f2 with respect to xy upon the Jacobian of f1 f2 with respect to uv. So let's find both of them. So Jacobian of f1 f2 with respect to xy is equal to determinant f1 with respect to x, f1 with respect to y, f2 with respect to x, f2 with respect to y. Let's put the values. Derivative of f1 with respect to x is minus 1. F1 with respect to y is minus 1. F2 with respect to x is minus 3x square. With respect to y is minus 3y square. So numerator is equal to 3y square minus 3x square. So 3 in bracket y square minus x square. So the second one, denominator f1 f2 with respect to uv is equal to determinant f1 with respect to u, f1 with respect to v, f2 with respect to u, f2 with respect to v. To u, to v. Oh, sorry. With respect to u is 3u square, 3v square. To u, to v. Please check the calculation. So the denominator here is 6 u square v minus 6 u v square. So denominator is equal to 6 common u v common in bracket u minus v. Let's put this. So 3 y square minus x square upon 6 u v u minus v. So this is the required thing. No, the question was wrong. That has to be. Any problem? So I guess no. Next example, if u cube plus v cube plus w cube is equal to x plus y plus z, comma u square plus v square plus w square equal to x cube plus y cube plus z cube. U plus v plus w is equal to x square plus y square plus z square. Show that Jacobian UVW upon xyz is equal to x minus y, y minus z, z minus x upon u minus v, v minus w, w minus u. What is our f1? U cube, v cube, w cube minus x minus y minus z equal to 0. What is our f2? U square plus v square plus w square minus x cube minus y cube minus z cube equal to 0. F3 u plus v plus w minus x square minus y square minus z square equal to 0. So Jacobian of u v w with respect to x y z is equal to minus 1 raised to 3 Jacobian of f1 f2 f3 with respect to x y z upon the Jacobian of f1 f2 f3 with respect to u v w. So I won't write down the formula now. I'll directly write down the derivative. What is the numerator? F1 with respect to x minus 1, F1 with respect to y minus 1, F1 with respect to z minus 1. F2 with respect to x minus 3x square, F2 with respect to y minus 3y square, F2 with respect to z minus 3z square. Third one minus 2x minus 2y minus 2z. So I'll use the properties of determinant T2 minus C1 and C3 minus C1. What do we get? Minus 3x square minus 2x. Minus 1 plus 1, this will become 0. Minus 3y square plus 3x square. Minus 3y square plus 3x square. Minus 2y plus 2x. Third one 0. Minus 3z square plus 3x square. And the third one minus 2z plus 2x. So the determinant here will be minus 1 in bracket minus 3 common in bracket y square minus x square into minus 2 common z minus x minus sign minus 3 common z square minus x square minus 2 common y minus x. So this is equal to minus 1 outside in bracket we'll have 6 y square minus x square into z minus x minus 6 z square minus x square y minus x. So 6 I can take outside, you will have minus 6 plus y minus x I can take outside. Y minus x, that is in both the terms. even z minus x is in both the terms, and in bracket what we have is y plus x, and there is this minus sign and z plus x. So if we solve this, plus x minus x will get cancelled out, y minus z will be there. With this minus outside, what I can write is 6 into y minus x, z minus x, and z minus y. And this is our numerator. Please see the calculations carefully. I'll give you 1 minute. Then I'll go for the denominator. Fine.
Sir,
Yes.
instead of solving like this with some other properties of determinant, we can directly reach the final answer without that much of calculation.
Fine. You can do that.
Thank you.
The denominator Jacobian of f1, f2, f3 with respect to UVW. So f1 with respect to u, 3u square, f1 with respect to v, f1 with respect to w, f2 with respect to u, 2u, 2v, 2w, f3 with respect to u, f3 with respect to v and w. Again, c2 minus c1, c3 minus c1. So 3u square, three v square minus 3u square, 3w square minus 3u square. So c2 minus c1, c3 minus c1. So 2u, 2v minus 2u, 2v, 2w minus 2u. Third one, 1, 0, 0. Again, I can interchange the rows, but when you interchange, the determinant is minus of whatever it was earlier. 1, 0, 0, 2u, 2 times v minus u, 2 times w minus u, 3u square, 3 in v square minus u square, 3 in w square minus u square. So denominator is equal to minus 1. I can take 2 common from the second row, 3 common from the third row, so that will become minus 6. In bracket, now let's solve the determinant. V minus u into w square minus u square minus w minus u, v square minus u square. Denominator is minus 6. I can take common. The things are v minus u will be common. W minus u is common. What remains is w plus u minus v. So that will be w minus v. Sorry. W plus u minus v plus u. So that will be w minus v. This is the denominator. Fine. So let's put these things there. This was a bit lengthy example, but still I took it because when you have to show that, so you have to use the properties, or else it will be very much difficult for you to bring these terms v minus u, u minus v, and v minus w. Of course, you can bring that, but calculations will be a bit tedious there. So minus 1, the numerator 6, y minus x, z minus x, z minus y upon minus 6, v minus u, w minus u, and w minus v. So this minus and this minus 6, 6. So I can take minus sign common from the first bracket of numerator and minus common from the first bracket of the denominator, and we get the required equation. I mean, not that difficult now to show this. Just minus signs are removed and you get the required. So I will simply write down hence proved. Fine. There is one type of example which actually I skipped because those examples are very much easier when we are dealing with this implicit functions. So we'll solve two examples of that kind. It is show that j into j dash is equal to 1. So example is verify j into j dash is equal to 1 for u is equal to xy, v is equal to x plus y. If you are fortunate enough that you get a chance to give M1 paper offline, then these type of examples are very much common in subjective exam. So how do we do that? Say, first of all, I will have to find j. So j is equal to Jacobian of uv with respect to xy. This will be determinant. U with respect to x, it will become y. U with respect to y will become x. V with respect to x, v with respect to y. So the determinant is simply y minus x. Now j dash. Jacobian of xy with respect to uv. So I'll do some calculations over here. So what I can have is actually I can find the function of x in terms of u and v, and as the it is verify, you cannot use that property itself. So I will have to simplify and get the function of x in terms of uv, and I'll have to get the function of y in terms of uv. That is one of the way. As this example is easier, it is possible easily. But still, we'll go by the implicit function. What does it say? So by Jacobians of implicit function, this will be Jacobian of f1, f2 with respect to uv upon Jacobian of f1, f2 with respect to xy. What is our f1 in this case? U minus xy equal to 0. f2 is v minus x minus y equal to 0. So this is equal to the determinant f1 with respect to u, f1 with respect to v, f2 with respect to u, f2 with respect to v. f1 with respect to x, f1 with respect to y, f2 with respect to x, f2 with respect to y. f1 with respect to u is 1, with respect to v is 0. f2 with respect to u is 0, f2 with respect to v is 1 upon f1 with respect to x is minus y, f1 with respect to y is minus x. f2 with respect to x is minus 1, f2 with respect to y is minus 1. So this is 1 upon y minus x. This is j dash. And so j into j dash is equal to y minus x into 1 upon y minus x. These two will get cancelled out and the answer is 1. So hence it is verified. Fine. This will be a homework for you. You can try this. Verify. J into j dash is equal to 1 for x is equal to u into v, u into 1 minus v actually, u into 1 minus v, and y is equal to u. Next example, if x is equal to v square plus w square, y is equal to w square plus u square, and z is equal to u square plus v square. Verify. So now we have three variables. Okay. First of all, let's go for J. J is Jacobian of XYZ with respect to U, V, W. So this is determinant of X with respect to U, 0, X with respect to V, X with respect to W, 2W. Y with respect to U, it is 2U, 0, 2W, 2U, 2V, 0. 2 can be taken common from each row, so you will have 8, 0 VW, U 0W, and U V 0. So the determinant is 8 UVW. Is it? So we'll have 0, 1, 1, 1, 0, 1, and 1, 1, 0. The determinant 0 into something, then 1 into minus 1 minus plus 1 into 1. So it is 2 actually. So this is 16 UVW. J. So to find J dash, we'll have Jacobian of UVW with respect to X, Y, Z. So which will be minus 1 raised to 3 Jacobian of F1, F2, F3 with respect to Jacobian of X, Y, Z upon Jacobian of F1, F2, F3 with respect to Jacobian of U, V, and W. So this is minus 1 into numerator में determinant F1 with respect to X. Let's write down F1. F1 is X minus V square minus W square. F2 is Y minus W square minus U square. F3 is Z minus U square minus V square. So F1 with respect to X 1, F1 with respect to Y 0, with respect to Z 0, 0 1 0, and 0 0 1. This is the numerator. And in the denominator, F1 with respect to U is minus 0. F1 with respect to V is minus 2V. With respect to W is minus 2W. F2 with respect to U minus 2U. 0 and 2W minus 2W. Third one. F3 with respect to U is minus 2U minus 2V 0. Look, the determinants looks same, this and this. Just you have to adjust some of the terms. You take minus common from all three of them, 3 rows. So we'll have minus 1 raised to 3, and this minus in the numerator will get cancelled out. And you have determinant 0, 2v, 2w, 2u, 0, 2w, 2u, 2v, 0. This is nothing but what we started with for j. This is 1 upon 16 u p w. So j into j dash will become 1. If you have any difficulty, you can ask.
Can you show the last slide in which you have given the homework question?
So I'll increase one more example here. Second, if x plus y plus z is equal to u, y plus z is equal to uv, and z is equal to uv w. Find Jacobian of xyz with respect to uv w. Fine. Put your name and roll number in the chat box if you haven't till now. Let's stop here. Fine. Thank you, everyone.
Sir,
Yes.
sir, what will be the syllabus for coming tutorial?
Syllabus for coming tutorial. What we have completed is partial differentiation. So we'll have tutorial on partial differentiation. Complete. Okay.
Oh, thank you, sir.